Okay, good morning, folks. So I have the quizzes ready to pass back. I'll pass them back near the end of the class. And the reason for that mostly is if I pass them back now, nobody listens. They look at their quizzes. So I pass them back at the end of the class. The first quiz, the average was a little low, which is not surprising because people don't know what to expect. It was 6.5. The second quiz, the average was 8.5. And that's kind of where I'm targeting, around the 8 area for the quizzes. That's what I'd like. I also took a check. The class average for this class in Organic 1 of the marks I could get was around 76%, I think. So that's what I expect the likely class average to be, somewhere around there for this class. Just letting you know, okay? So, so what we tend to have is the students that did less well in Organic 1 typically decide they don't like it and don't take this course. And you folks all love organic, so that's why you're here. So we've been talking about carboxylic acid derivatives, and we talked about these derivatives, and this is an important thing to remember, this reactivity order. These carboxylic acid derivatives are very reactive, actually. They're so reactive that they're not really easy to keep. When you make a carboxylic acid chloride, you know, it's pretty stable. You can keep it around for maybe days. You have to go through special, you have to make sure that it's dry, that there's no exposure to the ambient environment because the moisture in the air will react and convert that back to a carboxylic acid. Anhydrides are similar. They're a little bit less difficult to keep around, but they are difficult to keep around. But you can buy carboxylic acid anhydrides from chemical suppliers. They come in airtight bottles under inert atmosphere. And then as soon as you open it, you want to use it as soon as possible because you can't open and close it, they react. Esters are quite stable. In fact, we use a lot of esters for solvent. They're stable so long as there's not an acid around to catalyze their hydrolysis. An acid and water, it will slowly degrade. The other thing is that one of the products is an acid, so we talk about it being an autocatalytic reaction because when it reacts, it forms an acid which catalyzes further hydrolysis of the reaction. Amides are very stable, as I mentioned, lucky for us, right? Because they're very important biologically. They make up a lot of structures in our bodies. They make a lot of enzymes. So amide bonds are very stable, very important. So how do we, it's nice too because we can make any of these from these. As long as we're on this side, we can make it from one of its precursors fairly easily. So how then, if this is so reactive, and this is more reactive than a carboxylic acid, how do we make these compounds? So that's what we're going to look at today. How would we make this thing? We talked about that. Synthesis of acid chlorides. We have to use some fairly harsh reagents. This is thionyl chloride. Thionyl chloride is simply this compound. The other one is oxalo chloride. Okay? Why these work is that this sulfur and both of these carbonyl carbons actually are particularly electrophilic. This is electrophilic because this is also very much like an acid chloride. It's a very reactive acid chloride. This carbon is very electrophilic because not only is it a carbonyl compound, it's bonded to electronegative chlorine, and it has another carbonyl group right next to it which is bonded to very electronegative chlorine. So those carbons are very electrophilic. And they're so electrophilic that even weak nucleophiles will react with them. So I think I'll pull down because this irritates me. There we go. So how would we make this? Let's just react some carboxylic acid. In this case, we'll just use a generic one. We've already talked a little bit about sorry, that's a Cl, and that's a Cl. So we've already talked, we can, in this case, our carboxylic acid is going to be our nucleophile. We could use either one of these pairs of electrons to attack the electrophilic carbon. We're going to get to the right place. We've already talked a little bit about how this oxygen is actually a little bit more nucleophilic than this one. If you choose the wrong one, it's not going to matter too much, but this is the better nucleophile. And we get a compound that looks like this. Okay, is that right? Do I have, oh! And there we go. Notice that the only bond I formed is here, and the only bond I broke was the carbon-oxygen double bond on the carbonyl group. Now, what happens from here? Well, we can do a couple of different things, but one thing we can do is some base will come along and pull off this proton. Something pulls off this proton to give us this compound. So I'm just going to put minus H+, and that's the H+ that we're losing. And let's draw our compound. We have R, C. Now I have a double bonded O down here. I have a single bonded oxygen. I have this thing. Oops. Okay. Now what we can do is, like any nucleophilic acyl substitution, we're really just doing a nucleophilic acyl substitution on this, and this is our nucleophile. We're going to substitute it. So we're going to push it back. And now I have this compound. Okay, and I knocked off chloride. Okay, so we made this. We did a nucleophilic attack of a carbonyl carbon that has a chloride attached to it. We ended up removing a proton, doing a bit of a proton transfer, and then here this tetrahedral intermediate reforms a carbon-oxygen double bond. And look what we have here. We have something that looks a lot like an anhydride. And basically what we now have is chloride has been released and is nucleophilic. It's just going to attack this carbonyl carbon. It can attack any of the carbonyl carbons, but if we attack that carbonyl carbon, we just go all the way back. Okay? And if we attack this carbonyl carbon, it just ends up coming back to here because that's non-productive. When it attacks that carbonyl carbon, it's just going to reform and knock the chloride back off. So all of these are equilibrium reactions. Okay, but when it does attack this carbonyl carbon, we end up getting something that is productive. And we'll see why it's productive. Oops. So it could also go back, but why this reaction goes, I'll move this up, is take a look what happens now when we push the arrows. So we could push, when we push our arrows, we reform our carbon-oxygen double bond. If we kicked off the chloride, we just go back. But we can also kick off this thing, and then we end up getting a series of kind of bond cleavages that occur, and we form this thing, which is the acid chloride, which is what we want. What else do we form? We form CO2, which is a gas, plus CO, which is a gas, plus our Cl minus, and we formed an H plus way back here, so that the other product here is actually HCl. But look at this. In this reaction, we have one species breaks up to give us 1, 2, 3, 4. Huge increase in entropy. That's what drives this reaction. Okay? It's one thing to know the mechanism, we can push all the arrows, but now we want to think as physical chemists and say, this reaction doesn't look like it should be enthalpically favored. It doesn't look like it's going to be a huge gain in enthalpy, but there's a huge increase in entropy, and that drives the reaction to completion. Because to go back, all of these molecules have to meet again in the same vicinity. And that would be 1, 2, 3, 4 molecules meeting in the same vicinity, and that's very unlikely. So once this step goes, this reaction is driven by this final step, which is non-reversible. Similar thing happens with these other reagents, with the thionyl chloride, kind of the same thing. At the last step, you'll find that you get 3 molecules that are formed.
Here's the arrow from the bond between the 2 C's to the double bond and the O.
Okay, take a look at this thing. That one's easy, right? This is CO. Okay, that's one of the Lewis structures for CO. Good question. Because I think sometimes we see all the gases and everything and we assume that other gas is carbon dioxide. It's not, it's carbon monoxide. So that's why this reaction goes to completion. We can do the same thing with thionyl chloride, and I won't do our initial attack is there. And kind of the same thing happens. We lose a proton, minus H plus. And then we get to here. So notice this mechanism is very similar. Okay, and it's at this point where we attack the carbonyl carbon. Oops. And then we kind of get our, it's this, all these reactions are reversible, except for this last one. When we reform, we end up getting same thing. In this case, we only get three new molecules formed out of it. But this one is also enthopically a little bit more favored because we're forming the CO2. But that's what drives these reactions. So we can make, the nice thing about that is we use entropy to make a very reactive molecule, which we can then react with other compounds to make everything else in that series.
You can put the board on the top.
Sure. Oh. There we go. So this is showing, and notice how in your slides they're not using this as the nucleophilic center. They're using this. That is very slightly incorrect. Not a big deal because you're going to end up in the same place. You're going to end up with the same products if you happen to choose the other oxygen as the nucleophilic oxygen. Once we make our carboxylic acid chloride, we can then react that with lots of different things, carboxylic acids. Now this we don't do very often because we usually make the acid chlorides from the acid, but if we do this reaction in the presence with water around, it will just react with water to reform the carboxylic acid. That reaction happens very rapidly. We get carboxylic acid. What's our other product here? Anybody? The product, the inorganic product that I haven't shown. Just asking you to balance the reaction. What's the other product? Is there chlorine in the other product? And what else? HCl is exactly right. It's just HCl is the other product. The OH ends up on that carbon, and the other hydrogen in the water ends up reacting with the Cl. So this one too, I want to talk a little bit about this actually. Let's take a look at this reaction. And again, I want to talk a little bit about the fact that there's not necessarily always one correct mechanism. And sometimes we kind of take shortcuts because we remember that we know that protons can move around. Talked to Dr. Lukeman, and he's on it. He's going to get me a big eraser, he says, so we'll see if he can make that happen this year. So for an acid chloride to react with just water, we have our water molecule, and water's nucleophilic because it has oxygen, which has lone pairs of electrons, and we just form this thing. Okay. Now, this is showing a proton moving from here to here, and that would be a 1, 2, 3, 4 member transition state. So that's actually not likely to occur in one step. This proton doesn't just hop over there. What really happens is another water molecule will come. We have water there. We have lots of water there. So we can remember when we have lots of water, we can use another molecule of water, and it just pulls off that proton. And we'll do this. And then our other product is this thing, which can then just float around, when we format and come over here, and then we deprotonate that, and we end up with this thing. Now I'm going to put H2O here, but remember I just grabbed H2O because there was lots of it around. So H2O, we threw it in there and we reform it here. Now we can push our electrons and we're going to knock off the chloride. Then we have the chloride, and a lot of students will pull that final proton off with the chloride to form HCl, but that doesn't actually happen, right? Because chloride is not a very good base. HCl is a very strong acid. What actually will pull that proton off is a molecule of water will come along and pull that proton off. Sometimes we like to say the chloride is pulling it off because then it conveniently gives us the right stoichiometry and the other product, which is HCl. Well, if this is done in an aqueous environment, HCl is a strong acid and simply ionizes in water. So just some base pulls that proton off. And in this case, our base is going to be the water. And it just pulls that proton off to give us our final product. And I've dragged the chloride back over with it, okay? So this is fine, actually. What I would like to see you guys do in something like this is maybe tell me that this is just a proton migration. Because the proton can get from there to there. I've shown it as a series of steps, and a lot of times I'll stop doing that because at this point, we really want to recognize that protons jump on, protons jump off. And on a molecule which has multiple sites for protonation, there is probably one site that is more basic than the others, and most of the time that's where the proton goes. But just like in these other things, if the proton goes there, that may not be the species that then reacts to give us our final product, right? That may be an intermediate species that just goes back. When it gets on that whatever basic site that then leads to product formation, that's what happens, product forms. So even though most of the time it's going to go to the most basic site, what we have to be aware is those protons are very labile and will move to all the different basic sites at one point or another, and sometimes that leads to a very productive protonation that goes on to form products. So we can use these things, these acid chlorides, we can react them with alcohols to form esters. We can react them with amines to form amides, and we can react them with carboxylates or carboxylic acids even to form anhydrides. One of the things that you will notice in a lot of these reactions, when we form the acid chloride, and we use that in a lot of synthesis to make these other compounds, we often throw in either pyridine or something called dimethylamino pyridine. I'm going to erase this stuff up top in a second just so it's not in the way. And you'll talk about this more if you happen to take 3513 next year. But this compound, these things are decent bases. What makes them good in this instance is they're non-nucleophilic bases. Although they will react as a nucleophile, and there's a lone pair of electrons on that nitrogen, and it's actually sticking out. It's not part of the pi system. So these things actually are pretty basic. They can act as nucleophiles. They'll react with that, but then they're also very, very good leaving groups. So these things are used for two reasons. One, when they do react with this compound, they actually are more reactive than in itself towards the acid, okay? So they're used as kind of a catalyst. The other thing they're used for is just to sop up the acid that's formed, because we want to sop up this acid formed because this thing is still reactive, and we don't want anything with acid around. Any little bit of water would react with that. So the purpose of the pyridine or dimethylamino pyridine. As it turns out, this is 4-dimethylamino pyridine, and you'll often see that just called DMAP. The purpose of that is twofold. To sop up, it's kind of called a proton sponge. It just sops up all the acid as it's formed, gets it out of the way, and it can act as a catalyst. So we can form anhydrides by reacting acid chlorides with a carboxylate or a carboxylic acid in the presence of something like pyridine or DMAP to form anhydrides. Another way to form anhydrides, intramolecularly, they're a little bit easier because these 5 and 6 membered rings are fairly favored. We can form these simply by heating and driving off water. We'll usually do this in such a way that we have something around to mop up that water is formed or get rid of it. At 300 degrees, any water that's formed will come off. The same with phthalic acid. We can react it. Notice we're quite far above the boiling point of water, so any water that's formed gets off and we get this anhydride. And these go virtually to 100% yields. Conversion of acid anhydrides to carboxylic acids. This is the same mechanism over and over and over. All you have to remember is that this thing can now be a leaving group. And when that happens, we get 2 carboxylic acids. What's the mechanism? The mechanism is kind of the same. They're showing this under acid conditions. So here we protonate, we activate the carbonyl. We actually don't have to activate the carbonyl in this instance. Our water acts as the nucleophile and attacks the activated carbonyl group in this case to give us our tetrahedral intermediate. We get a proton migration, and then we can break up our tetrahedral intermediate, and when we do that, we actually get our carboxylic acid, and in this case another carboxylic acid, and finally we end up deprotonating at the end. So this is the same mechanism. Electrophilic carbon, some nucleophile, in this case water, attacks those, and it could attack either one of these, right? It's going to lead to the same products in this case. Those things can be converted to esters and amides, but we cannot convert an anhydride to a carboxylic acid chloride. That's going the wrong way, uphill. Remember, to get uphill, we have to use tricks like entropy to get us up the hill, and then enthalpy can drive the rest of these reactions. So we can make esters and amides from carboxylic acid anhydrides. Now the last thing I want to talk about is this Fischer Esterification. Do I have time? Yes, I do. Okay. This is a good example of something where we have a lot of protons jumping up and down. This reaction is a complete equilibrium reaction. So on the board, we're going to react a carboxylic acid with an alcohol in the presence of an acid catalyst. So what's the first thing that happens then with the acid catalyst around? I'm going to use acetic acid. Okay, and there's methanol around. I'm going to use ethanol. Well, actually, I can use ROH because it works in this case. Okay, that's what I have. What's the first step? What happens when we have not a bad electrophile? This carbon is not too bad as an electrophile, but it's not really good. We want to activate it. So we put a little bit of acid around, and we activate it by protonating it. And now we have our alcohol around. That is just going to be our nucleophile. And we realize that these reactions are all reversible. What do we want to do? Well, we want to move a proton. We can go back by just pulling off this alcohol, but we want to move a proton from here to one of there. Okay? And we can do that. Alcohol can come along and remove this proton. Another carboxylic acid come along and remove this proton. But the proton gets removed, and then something floats around and puts the proton on one of those oxygens up there. So we get and I'm not going to do, I'm just going to put it up there. There we go. So that's another way to just indicate I realize that this happens in more than one step. It doesn't just migrate because it would again involve a 1, 2, 3, 4-member transition state, not very favored. 5-member transition states, then you can get the migration occur easily. 6-member transition states occurs easily. So 1,4 and 1,5 proton migrations do happen intramolecularly, but this would be 1,3 proton migration, and those don't happen very easily intramolecularly. Now we've moved there, we should be happy because now we can push it off as water. And we get this thing, CH3, C, double bond OH plus, OR, and this can just lose water, or I'm sorry, lose a proton and give us our put the H2O in a box because I want it to end up over here as one of our products. So this reaction is completely reversible. What would I do if I wanted this as my product? I would probably do it with my, if possible, I would use my alcohol as a solvent. If it was a liquid, that would make a nice solvent, because then I have lots of alcohol, and that drives this whole reaction here. If not, I would use some organic solvent that I can keep dry, and the only water I have around is the water that's formed. And I might throw something in there, something we call molecular sieves, or another something else that will just soak up that water and remove it from the equilibrium and drive that reaction all the way here. Conversely, if I take an ester and I throw a bunch of water in and an acid, it's all going to go back to this. This is called the Fischer Esterification, named after Emil Fischer, chemist in the late 1800s, German chemist, did a lot in terms of discovering new reactions. And this reaction is used a lot to make esters. We just drive this reaction. The other thing we sometimes do, we would do this reaction, something like toluene. We reflux it, and we have the toluene going up, and in a trap, we can catch the water, and the water doesn't go back into the reaction because water is heavier than toluene. That's something called the Dean-Stark trap. So anyway, that's how we do these reactions. Again, the important thing here is that it is a complete equilibrium reaction. It can go one way or the other, and as the controllers of the lab, we can make it go towards one direction or the other, depending on what we want. We can start with a carboxylic acid and an alcohol and drive it to the ester, or we can start with an ester, a little bit of acid, throw some water in there, and drive it the other way. We can also make esters from acid chlorides. This reaction actually goes quite quickly. So, and in fact, when I was a graduate student, I had to make a lot of esters, and this was the method of choice because it was just a lot faster to take a carboxylic acid in about an hour. I could convert it to the acid chloride. Then I would just remove everything, throw my other compounds in, and in another 10 or 15 minutes, I would get this, and I'd be able to work it up. This is actually a more convenient route, but it's less environmentally friendly than the other route, although you have to take energy needs into consideration. So I think we're going to stop there for today, and I want to pass back the quizzes. And I'll pass them back because I do want to